Hello, welcome to Dreamwave Science, where curiosity is gently set down, and science takes a slow pace to bring us closer to sleep. Tonight, with you here, it feels warm. Feel free to relax in the most comfortable way for you, whether lying in bed, leaning back on the sofa, or simply sitting still as the room slowly quiets down. There's no rush here, and no pressure to understand everything immediately. We simply walk slowly through an idea, like a stroll under a quiet night sky, noticing each little thing, one by one. Tonight's journey begins with a thought that is both vast and very close. The idea of leaving home, not just leaving a house, a city, or even a planet, but leaving the entire solar system, the big family of worlds orbiting the sun, the one that has protected all humanity ever to have lived. It may sound dramatic, but it carries a sense of calm. The space doesn't roar when something moves away. It simply remains calm as the distance grows. In science fiction stories, we often see ships gliding through the stars, humans leaving and returning one day, like sailors crossing the seas and coming back to the familiar shore. That image is comforting because it resembles everyday life. You leave home, travel far, and then return. The ship sails and comes back to port. The plane crosses the continent and lands where it took off. Even with long trips, we are accustomed to believing that there will ultimately be a day to return. But space, it turns out, doesn't always operate like the ocean or the sky. In the physics of motion and energy, in the distance between stars, and in the fragility of the machines we launch from Earth, there's a very quiet yet very clear truth. Leaving the solar system might not be a trip you can easily make again. In a very real sense, it could be a one-way journey. I will touch on this idea slowly. No need to rush to a conclusion. Many things in the universe unfold slowly, layer by layer, and each layer carries its own story. Before we continue, let me ask you a light question. Where are you listening from tonight? A quiet apartment, a home where the rest of the world is already asleep, or somewhere you just want the outside sound to fade away? And what time is it where you are now? Late night, early morning, or that in-between time when the clock doesn't seem important anymore and thoughts flow more freely? It's interesting how the same moment can be felt in countless ways. Right now, somewhere on Earth, the sun is rising. In another place, rain is gently tapping on the window. And far above, beyond the thin layer of atmosphere, a few probes are still heading outward, slowly, but each second taking them further from home. If you find this type of quiet exploration suits you, or if it's simply a gentle way to close the day, I'd really appreciate it if you consider liking the video or subscribing to the channel. That helps this small, peaceful science corner reach others who are also seeking a quiet pause. But right now, you don't need to do anything. Just listen, breathe, and let your mind follow its own pace. I'll begin with something very familiar. Imagine you are standing outside on a clear night. The sky opens above you, filled with stars, and somewhere among them, a faint point of light is slowly moving, possibly Mars or Jupiter, silently drifting across the starry backdrop. In moments like these, it's easy to see space as an open expanse, as if all you have to do is want to cross it. After all, we've sent machines to those planets. We've set foot on the moon. We've captured Saturn's rings, sent robots to land on a comet. Step by step, the solar system seems to shrink, come closer, more like a map than a mystery. But the distances in space have a way of hiding their true scale. Numbers like millions of kilometers, billions of kilometers still sound reasonable, until we no longer have something familiar to compare them to. Driving across a continent is already long, but a ship crossing Neptune's orbit is a vast distance so huge that even light, the fastest thing in the universe, would need hours just to cover part of it. And after Neptune, after the outer planets, the solar system doesn't end like a door closing. It stretches into sparse and cold regions, where the sunlight thins and fades. There, objects drift in slow and lonely orbits, remnants from the time when the planets were still forming. Further out is a boundary not marked by lines, but by a fading, where the sun's influence weakens and the space between stars begins. Leaving all of that is not like stepping through a door. It's more like leaving an invisible current that has carried you your entire life. Gravity is part of that current. We feel it every day through the weight of our bodies, through the way things fall, through the force that holds the oceans in their basin and wraps the atmosphere around the planet. But gravity doesn't stop at the edge of the atmosphere. It extends outward, weakens with distance, but never fully disappears. The sun's gravity keeps the planets in orbit, makes comets return, and guides even distant pieces of ice in slow arcs that stretch over millions of years. So, to leave the solar system, you must completely overcome that pull, reach a speed large enough that the sun can no longer call you back. It sounds like all you need is to go fast enough. But speed in space isn't like pressing the gas pedal. Every increase in speed requires energy, and energy in space is very costly. Rockets must carry fuel, and every kilogram of fuel increases the mass, which in turn needs more fuel to push it. A fragile balance, like standing in a bucket and trying to lift yourself by pulling on the bucket handles. That's one of the very quiet reasons why going far is often easier than coming back. When leaving Earth, we can take advantage of the planet's movement, use the gravitational pull of other worlds, and calculate orbits to gain speed. Space agencies have done this very well, sending ships along curved paths, borrowing energy from planets as they pass by, like receiving a series of gentle pushes. But to return from the distant outskirts, you have to reverse almost the entire process. You must reduce an enormous amount of speed, carry fuel across distances with no refueling stations, no gas stations, and no convenient planets waiting to help. The farther you go, the harder it becomes to return, to the point that the idea of coming back gradually falls out of practical plans. This becomes very clear in the history of space exploration. The Voyager spacecraft, launched in the 1970s, are still traveling outward. They've crossed the region where the solar wind gives way to interstellar space. On the spacecraft are gold records, messages sent to some distant intelligence, should they ever encounter them. But there was never a plan to bring Voyager back. From the moment it left Earth, that journey was understood as one way. There's something very deep in this truth. The machines created by human hands are drifting in the dark, billions of kilometers away, not returning, carrying with them the faint echoes of our voices and music, heading into a future we won't be here to witness. And even so, Voyager is still slow compared to the standards of the universe. At its current speed, if it were to happen upon the nearest star, which it's not, it would take tens of thousands of years to get there. The space between the stars is so vast that leaving the solar system doesn't mean reaching somewhere. It's more like stepping off the shore into an ocean so vast you can't see the other shore, and may never touch any shore. This thought leads us to an interesting question. When we talk about leaving the solar system, what are we really talking about? Is there a clear boundary? A moment when you look back and say, from here on out, it's beyond? The answer is both yes and no. There are regions where the sun's influence weakens, where the solar wind fades, where particles from interstellar space begin to dominate. Science has named these boundaries, like termination shock, heliosphere, heliopause. But in reality, they are gradual transitions, not walls or gates. A ship passing through won't be jolted, nor will it see a sign. The change is very subtle. Only instruments and patient observation can detect it. So, leaving the solar system is not a single event, but a process, a gradual drifting away from warmth and light, from familiar orbits, from the steady presence of the sun in the sky. If you stop and imagine that journey, you might feel a very specific kind of stillness, the sun gradually getting smaller behind. At first, it's still a bright star. Then it's just a slightly brighter point among many others. The planets disappear one by one, until only darkness and distant stars remain. No sound, no wind, no waves, only the silent motion of a ship gliding through almost perfect vacuum. It's peaceful in some way, but it also has a sense of closure, because the farther you go, the harder it is to turn back. Not because nature has set a law of prohibition or a barrier. It's simply the consequence of distance, energy, and time. The universe doesn't prevent you from returning. It just makes it so difficult that, in practice, it almost loses meaning. And so we reach the heart of tonight's idea. Leaving the solar system is not impossible. On one level, we've done it with small robot explorers, but leaving in a way that you could still return, especially if it's something large, something that carries humans, is an entirely different matter. The physics of motion, the limits of propulsion, and the vast scale of the space between stars, all silently and persistently turn the departure into a one-way path. I will go through these reasons one by one, slowly, so that each fragment of the idea settles before we add the next. Understanding often comes more easily when it opens slowly, like the darkness outside the window deepening minute by minute. Right now, you only need to hold in your mind a simple image, a tiny probe that has traveled very far, past the planets on the edge, still silently gliding outward. No engine noise, no dramatic music, only the inertia carrying it, kilometer after kilometer, year after year. Behind it, the sun fades. Ahead, the stars are still so far they are almost untouchable. So why does the solar system often feel close? Like you could reach it? Even though it's actually so vast, why does it feel in our imagination like a region around home you can walk through, instead of the vast, enormous domain it truly is? Part of that feeling comes from how easily we forget the true scale of the environment around us, especially when familiar images in books, posters, or documentaries often arrange the planets neatly next to each other, like decorations on a shelf. Mercury is here, Venus is there, Earth is nearby, and then the giant planets are lined up outside. Our minds naturally take those drawings as a map that can be crossed with patience and determination, like going from one country to another. But those diagrams are more symbols than true proportions. If we shrink Earth down to the size of a marble, the moon won't hover right beside it just a few centimeters away. It will be more than a meter away, and between them will be a gap larger than most people imagine. Then Mars will be several tens of meters farther. Jupiter will be so far it needs to be measured in kilometers in that model. And Neptune, the distant planet on the edge, might be so far you'd need to drive to reach it. What fills the vastness between those worlds is not glowing mist, not drifting clouds, nor anything that evokes a sense of connection. Most of it is simply emptiness, so empty that a ship could fly for months without encountering anything significant. No landmarks, no nearby objects, no sense of movement, just the silent numbers on the instruments. And yet, the solar system still makes us feel close, like a region that belongs to us, a place we've started to explore and, in some sense, begun to understand. Part of that feeling comes from the steady rhythm of exploration over the past century. Every decade brings new images, new missions, new evidence that human technology can reach farther. The moon used to be impossible. Then it became a place with footprints imprinted on its nearly unchanging dust. Mars is the same, from a distant red dot to a terrain we can see in detail through the cameras of the enduring rovers. Small steps like that create a continuous feeling, as if going outside is just continuing what we've already begun. If we've reached the moon, Mars feels like the next step. If we've sent ships to Jupiter and Saturn, the outer edge of the solar system seems just a matter of time. But that steady expansion feeling can be misleading, because each step farther requires increasing effort that doesn't follow a proportion. Going to the moon takes days. Going to Mars takes months. Reaching the outer planets takes years. But to truly leave the solar system, it takes several decades. The distance doesn't increase linearly, it expands violently, stretching further and further until the scale no longer aligns with everyday concepts. Another reason the solar system feels within reach is because gravity itself, the force that binds the whole system, also helps us move within it. Spacecraft rarely fly straight. They follow curves, pulled and guided by the gravitational forces of the worlds along the way. This technique is often called gravity assist, allowing the ship to accelerate without carrying extra fuel. When flying close to a planet, the ship can borrow a small portion of that planet's orbital energy to change direction and speed up. This method is subtle and beautiful, like stepping from one moving conveyor belt to another, each time being gently pushed forward. Voyager used this technique extremely accurately, timing the launch so that the outer planets aligned in a rare configuration. One by one, the ship passed Jupiter, Saturn, Uranus, and Neptune. Each time it passed, it sped up a little more, changed direction a little more, then continued on its way toward interstellar space. Hearing this, it's easy to think of the solar system as a series of stepping stones, a network of gravitational roads that could take a traveler anywhere. On some level, that's true. In the planetary region, gravity can be used as a flow to make the journey more efficient. But the farther you go, the sparser and weaker those roads become. Outside the giant planets, there are no more large celestial bodies to continue aiding, only scattered pieces of ice. Too small to provide significant support, the useful flows gradually fade, and what remains is primarily the inertia of the speed you've already accumulated. That's a very quiet turning point in every journey far from the sun. Before a certain distance, the solar system still has structure, can be navigated, has landmarks, has assistance. Beyond that, it becomes a different kind of space, sparse and empty, where movement continues, but the guidance fades. The familiar feeling also plays a big part. All the planets orbit the same star, bathed in the same light, following predictable orbits. Everything has a pleasant order, like a stable cosmic neighborhood. Even asteroids and comets, once considered chaotic, are now tracked with incredible accuracy. Living in a predictable system creates a very light sense of security. Even though its size exceeds imagination, the sun rises every day. The moon waxes and wanes. The planets return to their familiar spots in the sky. Everything moves, but it always returns. And returning is the key word embedded in the human experience. The harvest returns. The migratory birds return. Ships return to port. The expectation of return shapes how we think about journeys, making even long trips still feel temporary. But the further you go into space, the less that expectation holds true. The distance is so great that the travel time is so long that the idea of returning gradually loses practical meaning. A ship leaving the solar system at tens of kilometers per second is very fast by human standards, but still slow by cosmic standards. At that speed, turning around to come back would require enormous energy and many decades, even centuries. Time becomes part of the calculation. A human lifetime is just a few decades. Civilizations change in a few hundred years, but the distance between stars, with today's spacecraft speed, is tied to thousands or millions of years. A journey longer than a human lifetime no longer feels like a trip in the usual sense. It becomes something else, a shift that's almost impossible to reverse. There's also a subtle factor that makes us feel still within reach, and that's communication within the solar system. Signals travel at the speed of light, about 300 km per second, fast enough that on Earth, we experience it almost instantly. Even with a ship near Mars, the delay is only a few minutes. You can't chat like on the phone, but you can still send commands and receive feedback in a reasonable amount of time. This creates a sense that even distant missions are still connected to us, still belong to the same operating world. Engineers on Earth send instructions. The ship responds. Data flows back. Images appear. Discoveries are announced. The connection is still there, and it nurtures the illusion that those distant places are still within reach. But as the distance increases, even light takes more time. Signals from the outer planets take hours to reach Earth. From the edge of the sun's influence, the heliosphere, the round-trip delay is more than a day. Communication slows down, no longer resembling conversation, but more like sending a message in a bottle drifting across the ocean. And eventually, In the space between stars, the communication delay could stretch to years. A message sent from the ship halfway to the nearest star may not receive a reply within the lifetime of the person who sent it. At that point, the connection becomes fragile, almost symbolic. The sense of being within reach isn't just about how far or near it is, but also about the ability to interact. When interaction fades, the sense that a place still belongs to our world also fades. We also need to think of the time scale, not just the spatial scale. The solar system is about 4.6 billion years old, and its structure changes very slowly, on timescales longer than human history. The planets follow their orbits with patient regularity. The sun shines steadily, only changing slowly over millions of years. To us, that stability feels like forever, as if the solar system is a fixed stage for life. But forever is sometimes just a misleading feeling. The sun is also moving through the Milky Way, dragging all the planets in a large orbit around the Milky Way. Right now, even if you are lying still on Earth, we are still rushing through space at hundreds of kilometers per second. The stars in the night sky aren't standing still either. They drift slowly, changing positions over centuries and millennia. In that sense, the solar system is not an immobile home, but a moving home, like a giant spaceship gliding through a vast ocean of stars. Leaving it, therefore, is not just crossing a boundary, it's stepping off a moving ship to enter an open sea that stretches in every direction. When you look at it this way, the illusion of closeness starts to fade, making way for a deeper understanding of what leaving means. It's not just about overcoming the sun's gravitational pull, but accepting that the place you're leaving continues to move, carrying everything familiar, while you drift along a different path. But gravity is not just a force that lingers here. It reaches far. It weakens with distance, but it never completely disappears. Earth keeps the moon in orbit, even though the moon is hundreds of thousands of kilometers away, and the sun, with a mass far greater than any planet, spreads its influence over billions of kilometers, pulling the entire solar system into a slow, shared dance. Every planet, every asteroid, every comet we've observed is moving within that gravitational pull. Even objects far away, where the sun's light has thinned to the point of barely being perceptible, can still feel this force, still follow the paths it quietly shapes. If you need an image to help visualize this, gravity is not like a string pulling directly inward. It's like a deep valley in the terrain of space itself. Everything tends to drift along the slope of that valley, unless it's given enough energy to climb out. The image of the valley is really useful. Imagine a ball lying in a shallow bowl. It can roll back and forth, but eventually, it will find its way to the lowest point. To take it out, you must provide enough energy to push it up the side of the bowl and over the edge. If you don't push hard enough, it will climb partway, then fall back to the center of the bowl. Leaving the solar system is almost like this, like pushing a ball out of an enormous, invisible bowl. The sun's gravity is that bowl, and everything inside follows its own path depending on its energy. Planets like Earth and Mars are not stationary. They are speeding along, simultaneously falling toward the sun but always sliding past it, creating a repeating orbit year after year. This detail is important because it reminds us that gravity doesn't just pull straight inward. Gravity, combined with motion, creates an orbit, a stable path that can last for billions of years. But orbits, no matter how beautiful, are still a form of being bound. Objects remain in the gravitational well, endlessly revolving, unless something changes their energy. To leave the solar system, a spacecraft must have enough energy to escape that well completely, not just climb high and then fall back, but to pass over the edge of the bowl and continue outward into infinity unless it intentionally expends energy to turn around. The necessary speed is often called escape velocity, but the name can sometimes mislead us. It's not a sudden burst of acceleration and then done. It's reaching a speed where gravity cannot slow you down to the point of stopping and pulling you back. From Earth's surface, the escape velocity is about 11 kilometers per second, faster than any airplane. Rockets must reach this speed to break free from Earth's gravitational pull. But escaping Earth is just the first step. On the scale of the solar system, the Sun's gravity is much stronger, and escaping it requires much more energy. Earth itself is orbiting the Sun at about 30 kilometers per second. This motion helps spacecraft, because if they leave Earth in the right direction, they inherit some of that speed. Like running on a moving conveyor belt rather than standing still, Earth gives them a boost. Even with that boost, escaping the Sun's gravitational influence still requires a huge amount of energy. Ships like Voyager can't carry enormous amounts of fuel, which would be impractical. So they rely on the gravity of giant gas planets to accelerate. Each close pass is like a slingshot, changing direction and increasing speed relative to the Sun. This technique works because the planets themselves are moving. When a spacecraft flies behind a planet along its orbital path, it can take a tiny fraction of the planet's momentum. The spacecraft speeds up, and the planet slows down by an amount that's undetectable for the planet. This change is negligible, but for a lightweight spacecraft, it can make the difference between being held back and escaping. Even so, these speeds are still modest by cosmic standards. Voyager 1, one of the fastest objects created by humans, travels about 17 kilometers per second relative to the Sun. That sounds fast, and it is fast by everyday standards. But at that speed, to reach the nearest star, if it happens to be heading in the right direction, it would take more than 70,000 years. The pull of gravity is not a wall you break through in an instant. It's more like a prolonged slowing down. As the spacecraft moves farther away, the Sun's gravity still pulls it back, gradually slowing the spacecraft bit by bit. If the spacecraft doesn't have enough escape velocity, it will eventually slow down to the point of almost stopping, and then begin to fall back inward, following a long, slow arc toward the Sun. Only when the initial speed is high enough will it continue outward. The velocity will still decrease, but it will never reach zero, even after escaping. The Sun's gravity will still have some effect. The path remains slightly curved, the speed still changing, but these effects weaken as the distance increases. This point is crucial because it shows something that is often overlooked. Gravity doesn't have sharp boundaries. There's no line you cross, and suddenly the Sun's pull disappears. It just fades, spreading out farther and farther, though weakening with distance. So, leaving the solar system isn't like stepping out of a door. It's more like moving away from a campfire on a cold night. The warmth decreases gradually. The light fades long after the fire has gone out of sight. A little glow may still be there. A little warmth may still be felt. A spacecraft traveling far from the planets is like that, still, in a subtle sense, within the Sun's reach. The pull is small, but it never entirely disappears. And there's another aspect that makes returning particularly difficult. To leave the solar system, a spacecraft needs enough energy to escape the Sun's pull, but to return, it must give up that energy, slow down enough to fall back in. Instead of continuing outward, slowing down in space is not easy. On Earth, air resistance and natural friction slow everything down. A car speeding up is slowed by wind resistance and rolling friction. But in the near-perfect vacuum of space, nothing naturally slows you down unless you actively fire engines in the opposite direction. This means that to return, the spacecraft must carry a huge amount of fuel to slow down, and that fuel must have been accelerated when it left, which means every stage of the journey requires more energy. The farther you go, the more energy is needed to remove in order to return, and the journey becomes less and less realistic. In that sense, gravity is like a one-way slope. Going down the slope, taking advantage of Earth's momentum and gravitational assists, is relatively efficient, but going up the slope, against the Sun's pull without air to slow you down, without nearby large celestial bodies to help, is much more costly. And there's another silent effect that only becomes clear when talking about very long distances. The solar system itself is moving through the Milky Way, orbiting the center of the Milky Way at hundreds of kilometers per second. A spacecraft leaving the solar system is not leaving from a stationary point. It's leaving from a moving point, and catching up with that movement after traveling very far will require extremely precise navigation, plus additional energy. After several decades or centuries, even a tiny error in speed or direction can expand into a huge distance. A spacecraft drifting in interstellar space will gradually realize that the solar system is no longer in the old position compared to the starry backdrop. So, returning is not as simple as turning around. It's calculating to chase a moving target, crossing vast distances. All of this makes the role of gravity in these journeys both subtle and profound. It's not just what keeps the planets in place. It's like the one who shapes the paths, the silent guide who decides what's easy, what's hard, and what's nearly impossible in reality. And it's also strange that gravity, the very thing that makes leaving the solar system so difficult, is also what keeps Earth in its stable orbit, maintaining the conditions for oceans to stay liquid, the climate to remain steady, and life to flourish. Without the sun's pull, Earth could drift into darkness, becoming a frozen world wandering among the stars. There's a quiet symmetry here, where the force that nurtures life also makes leaving forever one of the most difficult journeys imaginable. If you return to the image of that tiny spacecraft, year after year drifting outward, you can see gravity working in a very quiet way. There's no string connecting it to the sun, and yet, its movement is still shaped by that distant star. Its speed gradually decreases, so slowly that it's almost imperceptible, as it climbs higher and higher out of the gravitational well. Then, at some point, the sun's pull weakens enough that other influences begin to matter more, the gentle tides of the Milky Way itself. At that distance, the solar system is no longer the dominant force shaping the path, but reaching that point takes decades, and when it gets there, the spacecraft has traveled so far and is so committed to its path that returning will require an extraordinary amount of energy and time. That's why missions leaving the solar system have always been designed with no expectation of return. Engineers and scientists plan them as journeys outward from the very start, because they understand that once you overcome the invisible grip to leave, that very thing becomes the wall going back. And so gravity, silently and invisibly, stands at the center of turning the departure into a one-way road. It decides the energy needed to escape. It determines the difficulty of slowing down, and it stretches the timeline of any effort to turn back into something enormous. In everyday life, speed seems easy to understand. You push the pedal harder, and the scenery passes faster. A train is faster than a bicycle. An airplane is faster than a train. These differences, though impressive, still lie within a range our minds can grasp. The fastest airplane still only takes a few hours to cross a continent, and the distance remains within the familiar experience. But space changes the meaning of speed. The distances are so vast, and the forces at play are subtle but persistent. Reaching a certain speed doesn't just help you arrive sooner. It determines whether you can arrive at all. It decides whether you're still bound by a gravitational system, or whether you slip free of it forever. And this is when the concept of escape velocity becomes crucial. It sounds technical, but it actually describes something very intuitive. Escape velocity is the minimum speed you need to reach in order to overcome the gravitational pull of a celestial body without needing to push further afterward. Once you reach that threshold, gravity will no longer pull you back, even though it will continue to slow you down as you go farther. You can imagine this with a throw. If you throw a ball into the air lightly, it goes up a little and then falls back into your hand. Throw it harder, and it goes higher, but still falls back. Throw it harder still, and it still falls, because gravity keeps slowing it down until its upward motion stops. But if you throw it hard enough that the ball never stops, never changes direction, never falls back, that's when it has reached escape velocity. For Earth, that velocity is about 11 kilometers per second, roughly 0 kilometers per hour. But escaping Earth is still not escaping the Sun. Earth is still orbiting the Sun. So even though the spacecraft has left Earth's gravity, it's still deep within the Sun's gravitational well. To completely leave the solar system, You need to reach the escape velocity of the Sun, much higher than the velocity needed from Earth's orbit. Fortunately, the spacecraft doesn't have to generate all that speed on its own, because it already inherits some of it from Earth's movement, about 30 kilometers per second around the Sun. We don't feel it, but we are actually moving quickly through space. Even with that advantage, reaching escape velocity from the Sun still requires a huge amount of energy and very careful calculations. The rocket provides the initial boost, then planetary gravitational assists often become the deciding factor. Without them, the amount of fuel needed would be so large it would be unrealistic. What makes escape velocity important isn't just the number, it's the meaning behind it. Crossing that threshold changes the nature of the journey. Below escape velocity, the movement is still temporary. You can go very far, but eventually, the path will curve back and pull you in. Above escape velocity, the road opens up infinitely, and the orbit no longer forces you to return to where you started. And in practical terms, once you escape the Sun's grip, returning becomes much more difficult. To return, the spacecraft must dump enough energy to fall back in, essentially reversing the very condition that allowed it to escape. Reversing is always expensive. Engines are good at speeding up, but slowing down in deep space requires firing in the opposite direction, meaning extra fuel, which has to be accelerated with the spacecraft. Every kilogram for the return journey increases the requirements for the trip, and this cycle of increase grows very quickly. There's another subtle detail. Escape velocity is not a wall you step across at a single moment. There's no boundary line where you cross and the Sun's pull disappears instantly. It's an energy condition. If your total energy relative to the celestial body is positive, you escape. If it's negative, you remain bound. And the consequences of that difference can be surprisingly fragile. A few meters per second off, tiny compared to speeds of tens of kilometers per second, can decide whether the orbit is bound or escapes entirely. Once on an escape trajectory, the spacecraft is still being pulled by the Sun, so its speed gradually decreases, but it never reaches zero. And because there's almost no friction in space, once it reaches that condition and shuts off its engines, the spacecraft continues on, year after year, century after century, simply by inertia. That silent persistence is part of why spacecraft leaving the solar system feel like emissaries sent into the future, continuing their journey long after the people who launched them are gone. But escape velocity also reminds us of the limits of technology. Chemical rockets, the ones used for most missions, are limited by the energy of chemical reactions. They can be optimized, but they can't be made infinite. Propulsion systems like ion engines are more efficient in another way, pushing very slowly but steadily, which is better for deep space. But they can't lift heavy loads from Earth. Even when thinking of more advanced ideas, the energy problem remains. To go much faster to reach a star within a human lifetime is a whole different story, much bigger than just escaping the Sun. Therefore, right now, our spacecraft leave the solar system in a very slow, very persistent way, taking decades to break free, and thousands of years to even approach the nearest star. They are not fast travelers by cosmic standards, but they are the ones that don't turn back. And when we place gravity and escape velocity side by side, we begin to see the core of the one-way story. Going out is difficult, but you can rely on momentum and gravitational assists. Returning is a reverse problem, needing to slow down in a vacuum, needing more fuel, needing more energy, and needing to chase a target that is moving, because the solar system is not standing still. In our minds, the solar system is often drawn as something stable, centered, with the Sun stationary at the center and the orbits neatly arranged like rings. But the truth is more dynamic. The Sun is not still. Earth is not still. No planet is still. They are all moving, all rushing through space at speeds so great we don't feel them, simply because everything around us shares that movement. When viewed this way, leaving the solar system is not leaving from a fixed point, it's leaving from a moving point. And this makes returning not just about turning around, but about calculating how to catch up with a target moving in the greater dance of the Milky Way. Imagine you throw a ball to a person running across a field. You can't aim at where they're standing. You have to aim at where they'll be when the ball gets there. The farther the distance, the longer the ball travels, and the more fragile the prediction becomes. On an interstellar scale, this difficulty expands to the point where it's almost no longer the same kind of problem. A ship traveling for centuries must take into account that the stars are shifting, the solar system is still moving, and the gravitational influences from objects it hasn't encountered yet. Therefore, returning to the solar system is not just about turning around and following the same path. That old path will no longer lead to where the solar system once was. It will lead to an empty space, a region that the sun passed through long ago. To find home again, the spacecraft must align with the new position and velocity of the solar system, then adjust its orbit through vast distances with extraordinary precision. And all of this requires energy, in reserve, and systems that must operate steadily over time, scales much longer than any spacecraft has ever been designed for. There's another subtle layer of motion that starts to become important as you go farther. The Milky Way itself creates its own gravitational field. Inside the solar system, that force is too weak to dominate. But on an interstellar scale, it's significant. A spacecraft moving farther from the Sun will increasingly feel the gravitational field of the entire Milky Way, and also the occasional pass of a star or a molecular cloud. These effects are gentle but persistent. Over decades and centuries, they can bend the spacecraft's orbit just a little, pushing it off course in ways that are very difficult to predict perfectly. The farther you go, the more those small deviations accumulate, and when you have to redraw the exact path to return, all of those small errors become the price you pay. Altogether, this forms a quiet truth. Leaving the solar system isn't just about overcoming gravity or reaching escape velocity. It's also about leaving a system that is in motion to enter an environment where motion is the rule, not the exception. And there's something else, easily overlooked because it happens so slowly. The Sun itself doesn't maintain its current shape forever. Over billions of years, it will gradually brighten and eventually swell into a red giant, long after humanity in its current form has disappeared. The solar system we know today is just a temporary configuration in a much longer story. That doesn't change the reality of missions lasting decades or centuries, but it reminds us that even the most seemingly stable structures are part of an ongoing change. Nothing stays still forever, not even the stars. Reflecting like this changes the concept of a journey. On Earth, returning home is often returning to a place that is essentially the same as when you left. The house is still in the same place. The city might change, but it's still anchored to the same land. Even the movement of continents is so slow that a single lifetime doesn't feel it. In space, the scale is completely different. Home isn't anchored to a fixed point. It belongs to a system that is in motion. And the longer you go, the farther that system moves. There's a gentle paradox here. The solar system creates the feeling of a stable refuge, with predictable orbits, a familiar rhythm. Yet on the scale of the Milky Way, it's a traveler, carrying us across space in a journey that started billions of years ago and will continue long after we're gone. When a spacecraft leaves the solar system, it's not just leaving a location, it's saying goodbye to a shared orbit, stepping off a moving platform to enter an environment that is vast and constantly changing. This separation grows over time. Each year, each decade, the distance between the spacecraft and the solar system increases, not just because the spacecraft is moving farther, but because the Sun is still racing through the Milky Way. Eventually, the separation becomes so large, and the difference in velocity becomes so significant, that returning will require extraordinary amounts of energy and precision far beyond current technological capabilities. Therefore, the motion of the solar system itself becomes another silent reason why leaving is nearly a one-way journey. It's not a wall or a border, but a gradual divergence, an expanding distance in space and time, making the idea of returning less and less realistic with each passing year. If you ask where the solar system ends, The first answer most people think of seems simple. It ends at the orbit of the last planet. Neptune orbits the Sun at a huge distance, much farther than the warm regions that sustain life on Earth, and for a time, it was natural to consider that far orbit as the outer edge of our neighborhood in space. Crossing Neptune would surely be the beginning of interstellar space. But that neat picture, like many neat pictures in astronomy, turns out to be insufficient. The solar system doesn't end at Neptune, or at Pluto, nor at any clearly marked boundary. It fades, is out. The influence stretches out to regions so wide and sparse that we can barely pinpoint the exact moment of leaving home. To understand why, we need to ask what really makes the solar system. Is it the region where the Sun's gravity dominates most strongly? Is it the region that contains objects orbiting the Sun? Or is it the region shaped by the solar wind, a stream of charged particles blowing out in all directions? Each way of defining it leads to a different boundary, and none of those boundaries is close to the outer orbits of the planets. We might start with the solar wind because it creates one of the easiest to grasp boundaries. The Sun is not just a glowing ball. It constantly emits energy particles. These particles travel at hundreds of kilometers per second, carrying the Sun's magnetic field with them, and inflate a huge bubble in space called the heliosphere. Inside this bubble, the solar wind dominates the environment. It pushes outward, resisting the very thin atmosphere and magnetic fields of interstellar space, creating a region where the conditions are shaped more by the Sun than by the galaxy outside. Earth, the planets, and every spacecraft we've launched all lie within this massive invisible bubble. For a long time, the heliosphere was just a theoretical idea, but then Voyager 1 and Voyager 2 actually crossed its outer edge, a region called the heliopause. There, the influence of the solar wind weakens, and the environment begins to resemble interstellar space more than the space inside the solar system. This crossing was not dramatic. There was no visible line, no sudden change in scenery. The spacecraft only recorded changes in particle density and magnetic fields, subtle signs indicating it had entered a new region. It was like moving from one climate to another, with no clear landmarks, just a feeling that the atmosphere was a little different, while everything else remained quietly the same. Still, crossing the heliopause doesn't mean leaving the solar system in the gravitational sense. The Sun's gravity reaches much farther, to distances that are no longer measured in billions of kilometers, but in larger, longer, and colder numbers. Out there are still objects bound to the Sun, following orbits that take millions of years to complete. One place where this is clearer is the Kuiper Belt, a vast region of icy objects that begins just beyond Neptune's orbit and extends much farther. Pluto is in this region, but it's just one of countless objects, mostly small, dark, and far away, orbiting the Sun on slow, long paths. The Kuiper Belt is not dense in the usual sense. The distances between objects are enormous. A spacecraft passing through could travel for days or weeks without coming close to any celestial object. But it is still a distinct part of the solar system, a remnant from the time when the planets were forming. Beyond the Kuiper Belt lies an even more mysterious region, extending so far that it's hard to imagine. The Oort cloud. This is a spherical halo of icy objects that may stretch out to tens of thousands of astronomical units. 1 astronomical unit, the average distance from Earth to the Sun, is about 150 million kilometers. So, the scale of the Oort cloud almost exceeds any comparison in everyday life. If Earth's orbit were shrunk down to the size of a marble, the outer edge of the Oort cloud could be so far away that you'd have to travel a long time to reach it in that model. And yet, even at those distances, objects are still bound by the Sun's gravity, following orbits that take millions of years to complete. This shows that the gravitational boundary of the solar system lies far beyond the regions we have directly explored. Voyager 1 has traveled more than 160 astronomical units from the Sun, a staggering distance by human standards, but it's still far from what could be considered the edge of the Oort cloud, let alone its outer boundary. In a very real sense, we are still deep inside the solar system. Even when the farthest spacecraft have entered interstellar space, Realizing this can make one pause. The solar system is not just a group of planets, it's a vast region of influence, spreading out in all directions, fading like the edge of a continent sinking into the ocean. And because it fades like that, leaving the solar system is not a single event. It's a process that passes through many layers. Each layer contains less sun than the previous one. The solar wind weakens, interplanetary dust thins out, the number of objects orbiting decreases, the interstellar medium becomes clearer. Each step farther makes one thing clearer. Distance, not a barrier, is the obstacle. Not because something is put up to stop you from returning, but because the time and energy required to reverse direction grows with each passing year. And there's another technical but very human element that leads the way. In the inner regions of the solar system, the sun and the planets are landmarks. They are bright, they are clear, they give you the sense of being in an orderly system. But the farther out you go, the smaller and fainter those landmarks become. The sun shrinks into a bright point among many other points. The planets almost disappear unless you have incredibly powerful equipment. Just a tiny error can accumulate over many years to become a deviation of millions of kilometers. To correct that error, you have to burn fuel, and that fuel must have been carried from the moment you left. In addition, the farther out you go, the more you are influenced by things outside the solar system. The gravitational pull of passing stars, the tidal forces of the Milky Way, the pressure of gas and interstellar dust. These things are small, but over long periods, they become significantly impactful in a quiet way. So, leaving the solar system is like entering a desert that keeps growing and empties out with each step, rather than stepping through a gate. At first, returning seems within reach. The farther you go, returning becomes difficult. The farther still, it becomes almost impossible. And when you reach the furthest edges of the sun's influence, the idea of returning fades, like a memory rather than a plan, far beyond Neptune's orbit. Beyond the scattered worlds of the Kuiper belt, there's a region where the solar system begins to resemble a fading echo rather than a system with a clear structure. The sun still pulls, but the familiar architecture of the orbits and the names we know gradually gives way to something thinner, darker, and more patient. And when a spacecraft finally drifts beyond the furthest reaches of the sun's influence, beyond the heliopause, beyond the icy remnants of the Oort cloud, it enters what we often call the empty void. But calling it empty is only half right. It's not the absolute emptiness. It's an extremely thin, extremely quiet place, harsh in a very subtle way. Out there, there's still gas, thin enough to be hard to believe, mostly hydrogen, mixed with helium and a little heavier elements, forming the interstellar medium. And out there, there's still dust, particles smaller than smoke, fragments of carbon or silicate drifting aimlessly. Each individual particle seems insignificant, but when the spacecraft is traveling at tens of kilometers per second, each small collision becomes a hard hit by physical standards. A dust particle colliding at that speed can erode the surface, leaving tiny dents, making the protective layer weaker. In the planetary region, that's relatively rare and bearable. But moving through interstellar space for decades or centuries, the cumulative effect of countless micro-collisions becomes a quietly persistent danger. It's not the kind of risk that causes an explosion. There's rarely a dramatic disaster moment. It's more like gradual erosion. The surface wears down, instruments become less stable, the coating thins, tiny cracks appear, materials weaken under the cumulative effect of collisions, radiation, and extreme temperature fluctuations. And when things happen this way, you start to understand a very simple thing. In deep space, what's scary isn't always the big shocks. Often, it's the very small, very sparse, very slow things that have time to become irreversible. And so, when we talk about interstellar travel, we're not just talking about going far. We're talking about placing a technological object into a timeline so long that the very concept of maintenance becomes a luxury. On Earth, everything exists thanks to a network of care inspectors, replacements, fixes, Renewals. Out there, that network disappears. What remains is the original design, the quality of the materials, and the cold persistence of physics. Radiation, on the interstellar scale, is like an endless rain. It doesn't roar. It doesn't flicker. There's no moment of arrival. It just falls steadily, constantly, with particles that each carry a fraction of the energy from immense events in the galaxy. Inside the heliosphere, the spacecraft is still protected by a relatively small magnetic umbrella. Not perfect, not absolutely stable, but effective. Out there, that umbrella closes, and the environment becomes real in the interstellar sense. What makes cosmic rays dangerous isn't just that they're powerful, it's that they're random. You can shield against an average level of radiation, but a rare high-energy particle hitting the wrong spot at the wrong time could cause a failure when there's no one there to intervene. A small bit flip in memory, if not detected and corrected, can disrupt a command sequence, a disturbance in the sensor. If it happens at just the right moment, while the system is self-calibrating, can send it into an incorrect state with no one at home to pull it back. Scenarios like these don't always happen, but when time stretches across centuries, probability starts to change meaning. It's not if, but when. And then you realize something a little counterintuitive. In deep space, the big danger is not the thing you can see, but the thing you can't see. It's not a huge rock appearing in front of you, but the invisible erosion at the atomic level. It's not a crash like a car accident, but millions of gentle taps on the surface, each leaving a mark that no one notices at first. It's not a fire, but a gradual brittleness of insulating materials, a slow aging of polymers, a fatigue at the joints, a small drift in the sensor, growing over time because no one recalibrates it. Heat, in the vacuum, also contributes to this persistent harshness. Space is cold in the sense that there's no heat source from the surroundings, but because there's no medium to conduct heat, everything happens slowly and uncomfortably in its own way. The spacecraft doesn't freeze immediately. It cools down slowly, and that seems easier. But that slowness turns the problem into a kind of continuous balance. Inside the spacecraft, electronics generate heat, power sources generate heat. The spacecraft must radiate heat through surfaces designed to emit it outward. And during the long journey, that balance is tested not only by the environment but by time. The coating changes its properties. The reflective surface erodes. Radiators lose efficiency. Small details make the thermal system no longer as designed. You don't need a large discrepancy to run into problems, just enough to let a temperature-sensitive component operate outside its safety range for a long time. Not an immediate failure, just weakening, and then one day, at the moment you need it most, it's no longer strong enough. Positioning is the same. In the inner regions, guidance can rely on natural things, signals from Earth, the Sun, the planets, clear geometric landmarks. As you go farther, that geometry disappears. The Sun shrinks into a bright point. The planets are no longer observational objects, but data. In a model, when that happens, you guide using more abstract things, distant stars, the pulse of pulsars, extremely small measurements of apparent position. But an extremely small measurement is a fragile promise. It requires sensitive equipment, stable clocks, systems that remain accurate after decades of radiation and heat. And most importantly, it requires confidence that the spacecraft still understands what it's measuring. When everything relies on interpolation, models, and algorithms, a tiny error in the baseline can slip into a huge error in the result, like a line slightly off by a few degrees that, stretched out, will end up far from where you thought it would go. Communication is another story, but with the same nature. Signals weaken with the square of the distance. The antennas have to be aimed precisely. The transmitters need power. The receivers on Earth need to be sensitive enough to separate the signal from the background noise. When the distance becomes large enough, even light itself becomes waiting time. A command sent out is like tossing a piece of paper into a river and waiting for it to float to the destination. No exchanges, just sending. Then, much later, receiving a faint response. That delay changes the ethics of control. Nearby, we drive, far away. We only give initial directions and hope the system can maintain itself. The spacecraft, in some sense, becomes a technical organism that must survive on its own. It must decide when to turn off systems, when to prioritize heat, when to prioritize communication, when to accept losing a sensor to save power for something else. And every one of these decisions must be programmed in advance, by people who won't be alive when that decision truly occurs. There's a very real emptiness in this thought. Between the stars, there are no opportunities, no large planets to ask for a gravitational boost, no atmosphere to break, nowhere to shelter, repair, or resupply. What is carried is the entire world. What is lost forever. And over time, loss is inevitable, not because of poor design, but because all finite systems are eaten by time in some way. So when people say missions leaving the solar system are designed as one-way trips, it's not just because of fuel, not just because of escape velocity. It's also because of a colder truth, you might imagine, a spacecraft with enough energy to return. But it's hard to imagine a spacecraft still intact enough to make that return journey after centuries, in an environment that continuously wears down every component of it. And from here, the idea of one-way starts to carry a deeper meaning than just technical terms. It's no longer just about an orbit that doesn't close. It's the asymmetry of reality. Going out can be optimized, utilizing the momentum, using gravitational assists, taking advantage of the first decades when the spacecraft is still strong. But coming back will happen when the spacecraft is weaker, with less power, worn sensors, and the environment still as harsh as before. Returning is doing something harder when you're in worse condition. At first, in imagination, go and return seems symmetrical, but the universe does not favor symmetry. It favors inertia. It favors what has begun continuing unless you have enough energy to change it. And it favors time in a very quiet way. No violence is needed, just enough time. Perhaps that's why spacecraft like Voyager evoke a special feeling. They aren't like the vehicles we're used to. They're more like messages, once sent. You don't expect them to return intact. You just hope they travel far enough to say something before they fall silent. And even when silent, they keep moving, like a physical trace of a moment in human history, drifting through a space where everything else is much older than us. Viewed this way, one way is not a tragedy. It's more like a choice that fits the scale. Because between the stars, distance is not just a measurement of space, it's a measure of time. And when you travel far enough in time, the concept of return starts to change. It's no longer coming back to the same place. It becomes coming back to a different world, a different sky, a different civilization, even a different definition of home. And then, a silent question arises. It's not can we return, it's what do we return for? When everything has already moved on with the solar system, with the galaxy, with time itself, then perhaps you realize the simplest thing. Sometimes, the strength of a journey doesn't lie in whether it can return. It lies in daring to go to a place where returning no longer matters. The systems are also tested to endure radiation, extreme temperatures, and many years of continuous operation. But even so, time and the environment still leave their mark. Components age. Lubricants can move or evaporate in a vacuum. Materials change slowly under conditions that no test on Earth can perfectly recreate over long enough periods. Energy is another silent limitation. As you move farther from the sun, solar panels gradually lose their effectiveness, and deep space missions must rely on power sources that were designed to gradually deplete over time. As power wanes, devices gradually shut down. Heaters reduce output, transmitters speak less. The spacecraft continues to move, but its capabilities shrink, like a traveler gradually shedding their belongings. Not because they want to, but because if they don't, they can't continue. If refueling and repairs were possible, part of that wear could be managed. Propellant could be replenished. Worn components could be replaced. The energy system could be restored. But between the stars, there are no depots, no workshops, no infrastructure at all. And just building such a network would require resources and coordination far beyond anything humanity has ever done. Of course, humans have imagined ways out. A spacecraft gathering interstellar hydrogen with a magnetic field and channeling it into a fusion engine. Fuel depots scattered around, replenished with materials mined from asteroids or distant moons. These ideas are intriguing, and maybe one day they'll be feasible in parts of the solar system. But extending that infrastructure out to interstellar space would be an endeavor of an entirely different scale, almost a civilization burden, not just a mission. So for now, each spacecraft leaving the solar system carries with it a simple understanding. It will not refuel. It will not be repaired. It will not return. This is not failure. It is a design choice, an acceptance of the true terrain of the universe. Voyager was built with this acceptance from the beginning. Its mission was exploration, to send back whatever it could, and then continue going as long as its power allowed. Bring it back home was never part of the plan, because the cost of a round trip would be too great. There is a very quiet lesson in this. Not dramatic, not melancholic, just reality. Some journeys are made to go out, and sometimes exploration means continuing to go, not returning. This idea becomes sharper when we imagine human interstellar travel. A crewed spacecraft doesn't just need propulsion and fuel. It also needs air, water, food, radiation shielding, and a life support system that operates steadily for many years or even decades without resupply. Recycling could extend resources, but only if that recycling system doesn't malfunction for the entire journey. And if you want to return, all those requirements almost have to double, leading to increased mass and complexity, while the safety margins thin out. That's why most serious visions of interstellar exploration begin with automated ships. Machines can withstand the cold, radiation, and isolation in ways the human body cannot. But even so, the limits are still there: finite fuel, dwindling power, and reliability that cannot be negotiated. And behind all of this, there's a constraint even quieter than radiation, but heavier than propulsion time, not just as journey length, but as a part of physics. In everyday life, we feel time flowing evenly. A second is a second, whether you're walking or sitting still, but physics shows that time depends on motion and gravity. At normal speeds, the difference is so small that no one notices, but it's real. Atomic clocks on satellites and high-speed planes drift by measurable amounts, and systems like GPS must correct for relativity, or they'll gradually get out of sync. With today's spacecraft, this effect is almost negligible, because their speeds are far from relativistic. Voyager flies at several tens of kilometers per second, practically sharing the same time rhythm as Earth. But if one day we imagine flights to a nearby star at a significant fraction of the speed of light, relativity will become a key part of the story. Time on the ship will pass more slowly than time on Earth. It sounds like a gift until you remember what it means if you want to return. The faster you go, the greater the difference between your time and Earth's time. A round trip at near light speed could return travelers to an Earth much older than they are. It would be a return in space, but not in time. It would no longer be the same era. It would no longer be the same world. And even without reaching relativistic speeds, time still works against the return in a simpler way. The journey is longer than a lifetime, longer than a career, longer than the assumptions of those who planned it. When a spacecraft has traveled far enough to start thinking about returning, the place it left has already changed, not just because the solar system is moving through the Milky Way, but because history keeps moving. There, one way is no longer just a technical problem. It becomes a distance that cannot be fully described in kilometers. It's a distance of opportunity, of connection, of years that can't be gathered back. Long before the first spacecraft left Earth, humans knew the feeling of going to a place where the way back was uncertain, but leaving the solar system carries a different weight. It's not just leaving a country or leaving a planet. It's leaving behind the shared environment of all human life. The sun has risen on all civilizations. The sky has framed all stories. Realizing this doesn't come like a shock. It comes like distance, slowly, quietly. At first, Earth is still visible. Then it becomes a point of light. Then it's hard to distinguish between the stars. And eventually, home is no longer something you can look back on. It becomes a concept, a memory, a former coordinate stored in data. Deep space has no horizon, no weather, no sound, no familiar landmarks. The scenery changes so slowly that you can travel millions of kilometers a day. And outside the window still looks the same. For a robot, it's just an environment. For humans, it's isolation on another level, not just devoid of people, but devoid of shared rhythms of life. Dawn, news, voices, small shifts that create a sense of living in the same world. And with the growing distance comes a growing clarity. Not panic, just understanding. There will be no rescue. Every problem must be solved with what's available on board, and some problems simply cannot be solved. In deep space, safety is not a promise, it's a design constraint. And uncertainty is not an exception, it's the normal state. There's another psychological layer to leaving the solar system. The shared rhythm of time begins to thin. On Earth, we live in a collective rhythm. Day and night return together. Holidays come together. News spreads together. Joy and sorrow pass through a culture like a wave. Even when apart, we're still held within the same calendar, far from Earth. That rhythm thins. The spacecraft doesn't live with dawn like we do. The clock on the spacecraft still ticks, but those milestones gradually feel more like conventions than experiences. Time is measured by checklists, by system check schedules, by timelines stretching forward without familiar landmarks. Meanwhile, the world at home continues. People age, societies change, languages evolve, priorities shift. The farther you go, the wider the gap between the traveler's experience and life on Earth grows, not just physically, but emotionally. Cultural references fade, memories remain, but they're no longer updated. The traveler becomes the bearer of a preserved version of the world, while the living present continues without them. For a robotic spacecraft, that separation is more symbolic than personal. But we still can't help but assign meaning to these machines. We see them as messengers, and when the spacecraft sends its final signal, there's a very quiet farewell, not because it sees something, but because a connection has ended. That's why the one-way door image is so fitting. A door closing behind you isn't just a physical barrier. It marks a shift in state. At first, you can still return, though at a cost. Go a little further. It becomes harder. Go farther still. And the distance, energy, and time form something close to finality. What makes it psychologically heavy is not that it slams shut, but because you realize it's closing very slowly. And then, in the background of everything, there's a bigger frame. Humanity has always lived under the same sun, within the same gravitational domain, around the same planets. Leaving the solar system is stepping out of that shared context, literally. It's not just leaving a point, but leaving a context that has embraced all human life up to this point. Exploration is always about crossing boundaries. That doesn't make long journeys meaningless, but it explains why missions leaving the solar system are rarely told as round trips. They're told as journeys outward, journeys that accept the finality of distance, rather than trying to conquer it. And perhaps, long before the first spacecraft crossed the heliosphere's edge, there was a moment when a group of people forced themselves to think in an unfamiliar unit of time. Not years, not decades, but thousands of years, even millions. They realized that a man-made object could outlive the civilization that created it, and continue drifting through the galaxy when everything back home had changed. And from that thought came a strange decision. If a spacecraft is going to leave the solar system and not return, perhaps it should carry not just instruments. Perhaps it should carry a message. That message became the golden record. In form, it's just a very simple object, a disk with grooves. made to be read with a needle, but its purpose is anything but simple. It carries greetings in many languages. It carries natural sounds, wind and thunder, waves and bird songs, the beat of a human heart. It carries music chosen from many cultures and many centuries, and it carries images, encoded in a way that could be reconstructed, showing landscapes, animals, plants, human faces, along with basic scientific diagrams, including a map-like clue to where the disk originated. What's impressive is not just the careful selection, but the honesty about probability. The galaxy is vast. Voyager is tiny. The chance that any civilization will randomly find it is exceedingly low. Yet, they still made that disk. There's something very human in that gesture, not expecting a reply, but deciding to reach out even when a response seems almost impossible, as if the act itself held meaning, as if leaving a trace was a kind of dignity. The disk also reflects an acceptance of the journey's shape. No one planned to retrieve it. No one expected the spacecraft to return. From the beginning, it was understood it would go out until its power faded and the signals fell silent. In that sense, the golden record isn't just a message to hypothetical listeners far away. It's also a message to the future, a snapshot of how humanity once was, what it valued, and what it chose to present when imagining itself seen from far, far away. The spacecraft themselves were built with that same spirit of living long, resilience, durability, the ability to operate beyond the expected lifespan. But even so, the designers knew in the end, time would win, power would dwindle, devices would fall silent, communication would end. And yet, decade after decade, Voyager continues to speak, not forever with dramatic images, not always with major discoveries, but with something more subtle, with measurements of particles and fields, with news quietly sent from a region no one has ever directly touched. Their signals grow weaker, but they carry a strange weight, because every transmission is proof of perseverance, proof of distance, proof that something created by us is still out there, still moving, still counting time in its own tranquil way. There's a stillness when imagining their journey now. They no longer visit planets. They pass through a place where changes are measured by very small shifts, not by landscapes. That rhythm is slow, almost meditative, but its meaning grows, because they are no longer just probes. They are the first objects ever made by humans to enter interstellar space, the first to leave the neighborhood near the sun and continue on, with no possibility of returning in any practical sense. That has never been called a failure. It's just the nature of the mission. The goal is to go, observe, transmit whatever can be transmitted, and then continue outward as long as the physics and dwindling power allow. Returning has never been in the plan, and there's a very quiet truth in that. Not every journey is born to be traced back. Some paths lead to places where returning will be so costly that no benefit justifies it. At that point, the value lies in what is learned along the way, and in what is carried forward. The golden record embodies that spirit. It is not a tool for coming back. It is a companion for leaving, a small symbol of a world that is alive, affixed to a machine that one day will fall silent, but still continues to drift. Even the choice of material reflects that long-term perspective. Gold was chosen not because of its beauty, but because of its durability, because it resists corrosion, because it can remain stable for a very long time in a vacuum, protected by a protective layer. In the best-case scenario, it could remain readable far longer than any human institutions, longer than any language we speak today could retain its form. This means the disk is not only a message for others, it is also a mirror for us, a reminder that when we imagine ourselves being explored, we inadvertently reveal what we believe is important, not what we are most proud of in the present moment, but what we hope will still be recognizable when everything else has passed. Thus, long after Voyager falls silent, long after its electronics have ceased and its transmitter has turned off, these disks may still exist, drifting through the galaxy as patient witnesses. They may never be found, but they may still exist. Despite that, as silent witnesses to a brief moment in human history. Thinking about this might make the night sky feel different. Amid countless stars, there are now two small objects made by humans, each carrying a tiny archive of Earth, quietly drifting outward. They are so far that it's hard to imagine, yet they still belong to our story. Like threads stretching from the present to a future we will never see. Their journey also serves as a reminder that leaving the solar system is not just an idea. It has happened. Objects made by humans have already and are continuing to move beyond the sun's farthest reach, on orbits that will not bring them back. And realizing that gently leads us to a question that typically arises after the wonder fades. If the one-way nature of these journeys is so well understood, why were the missions designed this way from the start? Why did engineers and scientists set out on paths leading outward without including return in the plan, even as a hypothesis? At first, it might seem like excessive caution or a lack of ambition. One might think that the future will change everything, that one day spacecraft will go out and then return, like ships once crossed oceans and began doing so more frequently. But when engineers and physicists talk about missions beyond the solar system, the story rarely revolves around coming back. The reason is not fear, not pessimism, but physics, a set of silent rules that govern movement, energy, and how matter behaves. These rules are not obstacles put in place to stop us. They are simply the conditions of the universe we live in. And when we look closely at these conditions, the idea of coming back begins to seem not like a difficult project, but like a problem that expands exponentially with every kilometer traveled. The first reality is the price of changing velocity in space. Speeding up and slowing down are not two symmetrical actions that can cancel each other out with no consequences. Each action requires propellant, and propellant has mass. If you want fuel to slow down later, you have to carry that mass from the start. Carrying more mass makes the launch heavier. A heavier launch requires more fuel. The feedback loop tightens quickly. This is not just a matter of clever design. It's part of the mathematics of rockets. No matter how efficient the engine is, the amount of fuel required for large changes in velocity increases rapidly as mission requirements increase. For journeys far beyond the planets, the fuel needed to leave, turn around, and return becomes so large that launching from Earth becomes extremely difficult in practical terms. Then there's timing. In the inner regions, missions can rely on orbital mechanics. One waits for the windows to align for low-cost travel. Going to Mars, for example, is always tied to times when Earth and Mars are in favorable geometric positions. But once you go beyond the outer planets, those opportunities become rare. There are no large celestial bodies nearby to assist gravitationally on demand. There are no reliable steps waiting at the right moment to reduce the cost of turning around. A spacecraft in interstellar space must almost entirely rely on its own propulsion system to slow down, turn, and then accelerate again. Every step costs energy, and every step requires the machinery to still be working after decades or even centuries. And even if energy is not the only issue, uncertainty will be the next challenge. Navigating across billions of kilometers requires extreme accuracy. In interstellar scale, even small deviations become huge distances. A small fraction of a degree close to home might not matter, but after many years of travel, it could cause you to miss your target by millions, even billions, of kilometers. In the solar system, small adjustments can correct that drift, but every time you correct, you consume fuel. The farther you go, the more you have to break down each remaining bit of propellant, and the mathematics becomes less forgiving. Returning means returning to a moving target. The solar system does not sit still, waiting for you. The planets continue to orbit, and the entire system continues its long rotation around the Milky Way. Coming back isn't about aiming for where Earth used to be, but about catching up to where it will be when you arrive, while matching both position and velocity. In principle, planetary motion can be predicted over long distances, but in practice, a round-trip mission requires continuous monitoring, constant corrections, and stable long-term navigation systems. While fuel is finite and communication delays grow, The environment itself also adds pressure, radiation, micro-collisions, thermal cycles, and material aging wear down the spacecraft over time. The systems designed for a few decades are not automatically suitable for centuries. Power diminishes, electronics accumulate damage, materials become brittle, the probability of failure increases every year. Backup systems can reduce risk, but backups add mass, and the fuel equation returns. Communication delays make everything heavier. A spacecraft far away can't be driven minute by minute. It must operate autonomously, deciding when to adjust its orbit, when to manage faults, when to perform complex burns without real-time supervision. For a return mission, that level of autonomy must be trusted for long periods, to the point that those who designed the spacecraft, even the organizations that built it, may have long disappeared. There's another asymmetry in performance that is easy to overlook. When going out, the spacecraft can borrow momentum. It takes advantage of Earth's orbital speed and gravitational assists from the planets to gain energy without carrying it all in the form of fuel. But when coming back, those assists might not be repeatable. The approach angle could be wrong. The timing might not align. The geometry might not allow the same push and pull sequence as the outbound journey. Without them, the fuel requirement increases again. And even if one day we have propulsion systems far beyond what we have today, the underlying truth remains. To return, you must shed the kinetic energy. You must slow down. In space, energy doesn't just dissipate like a car driving on the road. It doesn't disappear into friction. It must be pushed out actively, often in the form of a thrust. The faster you go, the more energy you need to shed, and the harder the mission becomes. That's why many serious interstellar concepts focus on one-way spacecraft. Accelerating once and drifting is far more practical than designing a vehicle that can turn around after going too far. And then there's a philosophical layer that follows, but it naturally arises from the practical side. Exploration doesn't always require coming back. The value of the mission lies in what it reveals and in what it sends back while it still can. Data transmitted across billions of kilometers can be far more valuable than retrieving a machine. Engineers plan for the phase when communication is still possible, understanding that silence will eventually come, and technology itself changes the meaning of long journeys. A spacecraft launched today could be surpassed by one launched decades later. In interstellar plans, there's a quiet issue called obsolescence. If a spacecraft takes centuries to go out and return, it may come back to a world that has already moved on with new tools or no reason to wait. So, the lack of a return plan is not a lack of courage. It's an acknowledgement of how distance, energy, uncertainty, time, and the environment add up. A one-way mission is still feasible and rich in scientific value. But a return mission beyond the solar system is not just hard. It's like a cost that grows exponentially. And yet, the idea of going forever still feels very abstract at first. Most journeys in life carry an assumption of symmetry. Go and return, far and meet again. Even long separations often end in reunion. But the further you look, the more that rhythm fades. Not abruptly, no dramatic borderlines, just the slow accumulation of facts. Gravity, energy, time, machines age, signals weaken, the spacecraft drifts outward, and with each passing year, the path behind it becomes harder to retrace. But within that, there is no tragedy. It's just the nature of this kind of journey. If you stand on Earth at night and look up, space may seem like a still background, but right now, objects made by humans are traveling in that darkness, small and faint, farther from the sun than any explorer in history. They don't rush, they don't struggle, they just move, carried by inertia, on orbits that will last long after their creators are gone. Those spacecraft don't feel the departure like we do. They don't feel the distance. They don't feel time, but thinking about them opens up a reflection, not just on technology, but on the meaning of exploration when the path doesn't bend back. Because while still in the solar system, everything feels connected. The sun rises and sets. The moon changes phases. The planets slowly drift across the sky. Even if we never leave Earth, we still live in a shared structure, under the same star, within the same gravitational rhythm, moving through the Milky Way together. Leaving that structure is stepping out of a shared story, going into a place where the sun is just another star, and home becomes something remembered, not something visible. This thought may make us waver at first, but it can also bring peace. The universe is vast, and movement within it is natural. Stars drift, galaxies collide and merge, and even the atoms in our bodies were created in distant places, having traveled through unimaginable distances before becoming part of this world. In that sense, leaving is not an exception. It's a continuation of a much older story, starting long before Earth formed, when clouds of gas and dust moved and slowly coalesced into stars and planets. Perhaps the difference lies in this: now we are aware of the journey, and awareness changes how we live with distance and time. A spacecraft drifting beyond the solar system is not just an object in motion, it is a reminder of how curiosity can take us far, that questions asked on a small planet can lead to journeys measured in billions of kilometers. And while these journeys reach outward, the meaning of home becomes clearer, not faded. Home is not just a point in space. It is a network of relationships, shared experiences, memories, and stories. It is where time is measured in familiar ways, where voices reach without delay, where the sky, the earth, and the air create a seamless living environment. A spacecraft leaving the solar system cannot carry those things with it. It only carries instruments, data, and silent structures built to endure. It moves through a region with no weather, no sound, no seasons, only steady time and the faint light of distant stars. And that contrast highlights something essential about exploration. The farther you look out, the more you understand the rarity and fragility of where you came from. Earth is not just a speck in space. It is a world of oceans and clouds, forests and deserts, countless forms of life sharing a thin layer of atmosphere, warmed by a single star, seen from very far away. It is small enough to seem fragile, but it holds everything we've ever known. Leaving that world, even just in imagination, can make us appreciate its uniqueness. And then there is another quiet realization, following when we think of journeys that do not return. Not every path requires a turn back. There are experiences, once lived, that stay behind. There are moments, once past, that can only be revisited through memory. This is not to lament. It is simply the nature of time. In a way, every day is a one-way journey. Each dawn leads to a sunset that will never repeat exactly. Each year takes us forward without ever pulling us back. The difference with leaving the solar system is just the scale. The principle is the same. And thinking about that sometimes brings an unusual comfort. The universe is not only built from loops but from change, from motion, from events that do not repeat. A spacecraft drifting outward is a very real embodiment of that. It moves forward, never back, carrying traces of its origin, but not bound to return. And as it moves, the distance grows until even light takes years to cross. The message, if still there, will arrive as faint echoes of a moment past, fragments of the past arriving late just as we are ready to hear them. Then even the echoes fade. The spacecraft falls silent, not because it stops moving, but because its voice has become too faint to hear. But the journey continues. There is a deep peace in that image, a silent traveler moving through the dark, guided only by the laws of motion, carrying a tiny fragment of human history. It's not in a hurry, it doesn't struggle, it simply moves, year after year, century after century, like a quiet witness to the vastness. Thinking about such journeys can change the feeling of the night sky. The stars are no longer just distant points, but places where paths have started to reach. However slowly, and at the same time, the solar system becomes more precious, not because it's the center of the universe, but because it's the center of our story, the place where consciousness emerged and began to ask about the stars. Leaving it forever is not something to fear. It is just one of the ways the universe unfolds, one of the paths that matter and energy travel. And right now, we are still here, on a small planet, under a familiar sky. The sun still rises, the night still carries stars, and those faraway spacecraft continue drifting, out of sight, reminding us that exploration does not always mean return. And sometimes the value of the journey lies in the path itself. If you are listening to these words in a quiet moment, perhaps you can imagine those two travelers moving outward, their paths stretching into the night, not hurried, not ending, and in that image, there is no urgency, no loss, only a gentle awareness of scale, of distance, of time still flowing forward as it always has. The universe is vast, but it is also tranquil in its own way, patient to infinity, allowing journeys to unfold over thousands, millions of years without haste. And here, on Earth, in this quiet moment, you too belong to that same universe, sharing the same stars, the same slow movement through space, the same steady flow of time. So, as the night deepens and the world settles, you can let that thought rest quietly. Everything moves, everything changes, and even the longest journeys begin from such very quiet moments like this, when the mind is still and the sky is full of distant stars. In silent,